In this video, we're going to be discussing AVL trees. So what you do when you have AVL trees is first you have to look at your tree and you're going to have an unbalanced node. Your unbalanced node is going to have a balance factor of either positive or -2. Then from this, you are going to be able to decide which side is heavy. And then after that, you need to look at the direction of the child subtree. And all these are going to tell you whether you have a left-left, right-right, left-right, or right-left case. So how do you find the unbalanced node? For number 1, to find your unbalanced node, that's going to be using the balance formula, which is going to equal to the height of the left minus the height of the right. For AVLs, your balance factor always has to be less than or equal to 1. So if you have a balance factor that is equal to +2, that's going to be left heavy. And if you have a balance factor that's equal to +2 is left heavy, and -2 is that's going to be right heavy. So the unbalanced node, you can also call this as Z, your Z node. After this, you need to find the child node. So you're going to have your Z, your Y, and your X. Z is your unbalanced node. Y is your child of Z on the heavy side. And X is the child of Y, is the child of Y in the direction of imbalance. So your structure is usually going to be something like this. It's going to be Z, Y, X, and then in some order like this. In a variation of this. So let's talk about our specific cases. So in case 1 is going to be your left-left. So this means that the reason why it's called left-left is because the majority of your graph is going to lie on the left side. So you're going to have Z, Y, and X like this. And that's your positions that they're going to be at for each of the identifying nodes that you have to see. So these are the nodes that you're going to have to identify, and then based off of which one it is, Z, Y, or X, that's going to tell you which one you're going to have to rotate in order to fix this tree that is unbalanced. So for example, if we have 30, 20, and 10, we can calculate our balance factors here. So to calculate our balance factors, we're going to have to take the heights. So you're going to have the BF of node 30 is going to be equal to +2. The balance factor of node 20 is going to equal to +1. So as I can see here, because we have a balance factor that is 2, that means that you are having a tree that is not fulfilling the AVL case. Therefore, there's something that we have to do in order to rotate it to get to that requirement of it being less than 1. So this means we're at a left-left case. So how do we fix this? Well, the way that you fix this is you have to rotate right on Z. So in your left-left case, this means that you have to perform a right rotation on your Z node. So as you can see here, you have Z, and that's going to be the node of your focus. So you're going to take this 30, and then you're going to rotate this right. So right would mean this way, aka you could say clockwise. So after you do that for this, it's going to look like this. You're going to have 10, 20, and 30. And this makes sense because now our tree matches the AVL property of having each of these nodes having a balance factor that is less than the absolute value of 1. And we can also see that it satisfies the binary search tree requirement, where all the values of the nodes on the left side of the root are less than, and on the right side they're all greater, because 10 is less than 20 and 30 is greater than 20. So now let's move on to our second case, when you have case 2. So case 2, this is when you have a right-right case. Right-right just means that you have a majority of your tree on the right side of your node. So you're going to have, of your parent node. So you're going to have z, y, and you're going to have x here. And an example of this is going to be 10, 20, 30. We can see initially it also matches the initial conditions of a binary search tree where all the values on the left are less and all the values on the right are greater. So now we have to calculate our balance factors and see exactly why this is not an AVL tree. So the balance factor of 10 is equal to -2. The balance factor of 20 is equal to -1. So after this, what we need to do when we have this right case is we are going to perform a left rotation on z. So what you're going to do is you have your 10, 20, 30 like this. So let's highlight z and you're going to turn this node to the left. Be careful and listen to the wording. Left rotation on z means you take the node of z and you rotate that node to the left. So then how is our tree that is unbalanced going to look like? Well, we're going to take this 10 and we're going to rotate it to the left. And then it's going to look just like our other tree. Now let's do our left-right case. So a way you can remember is when you have a combination of different directions, that's how you can remember that you have to do 2 rotations in order to restore the balance to be an AVL tree, your balance factor to be an AVL tree. So in a left-right case, you're going to have this is your second category. This is when you have a angled tree. So here, let's say we have something that is z, y, x. So it means that it's going to be heavy on the left side and the child is going to be on the right. So the root node and also the child is going to be on the right, but it's going to be heavy to the left. So an example of this would be if we had a tree that was 30, 20, and 25. So if we connect these, that's how it's going to look like. Now we're going to calculate our balance factors. Our balance factor of node 30 is going to be equal to a +2, and our balance factor of our node, that's our balance factor for node 30 is equal to +2. The balance factor of our node 20 is equal to -1. So we're going to have to perform 2 rotations in this case. First, you're going to do a left rotation for y, and then you're going to do a right rotate of z. So how that's going to look like is here, this is going to be converted to this form, 20, 25, and 30, because we can see that in this case our y is going to be here, and we can see that our z is going to be up here. So as per our definition, we're going to turn this one to the right and we're going to turn our y to the left. So when we do that, we're going to have our step 1. Our step 1 is going to be a left rotation of y. So we're going to turn this one this way first. And then after we do that, we get this case where we have our 30 here and we have our y down there. And then after this, what we have to do is a right rotation on z. So our z is now over here. So you're going to have to turn this one to the right. So the step in between this was you had a 30 here and your 25 here, and you had your 20 here. So this is your final result. And this is your intermediate step. So here your 20 is here and your 30 is up here. So that was why we see that all the way down there, and then your 30 is up there, your 25 is there. And then after this you take your z was this one, and you rotate it to the left. So that's how we got or we rotated to the right, so that's why it went down there. That's your final result. Okay, so now let's talk about your right-left case, RL. So what this means is that you have your heavy pattern on the right and your child on your left. So your heavy side is the side that comes first, and then your left is the side of your child. So you're going to have, for example, Z, Y, and X. And our example here is going to be 10, a 30, and a 20. So let's calculate our balance factors. Our balance factor of 10 is equal to -2, and our balance factor of 30 is equal to a +1. Now, our rotations that we're going to do on this case is we are going to do first a right rotate of node Y, and then our second step is going to be a left rotate of node Z. So upon our first step, we can color in what our Z is here and what is our Y here. So the first thing we have to do is take Y. We're going to take Y and turn it to the right. So this is going to result in us having 10, 20, and 30. And then after this, let's color in again our Z and our Y. So now after this, we have to take our Z, and our Z is this 10 here, and we have to rotate that to the left. So if we do that, you're going to have a 10, 20, and a 30, and we can see that all 4 of our cases, it all turned out to the same binary tree that is an AVL tree in the end, because we only have 3 numbers, and also that is what it would look like when it's balanced, where 20 is your root node and 10 and 30 are your child nodes on the respective left and the right side. So yes, whenever you have a straight line like this where it's heavily skewed, that's how you know it's going to be a case where it's going to be in the same direction. But when you have an angle inside of, or a kink inside of your tree, that means that you know that it's going to be a combination of different directions, and it's going to require 2 rotations. Here we only are required to do 1 rotation in order to restore the balance. So that's how we can tell what to do. Right rotation, left rotation, and overall, don't just rotate this one once, you have to rotate this one twice.